In the earlier discussion, we have discussed the condition and the sufficient condition for the validity of differentiation and integration under the integral sign for the case of proper integral. That means when the limits of integration are finite numbers or none of the points in this integral from a to b are a point of infinite discontinuity. Now, in this video, I'm going to explain to you the uniform convergence of improper integral, because that condition will be the sufficient condition for the validity of differentiation and integration under integral sign for the case of improper integral. Now, what are improper integrals? Improper integrals are of this type only. Phi of y is called integral a to infinity, where at least one of the limits of the integration is infinity, or it can be phi of y is called integral a to b fxy dx, where a is a point of infinite discontinuity of this function fxy. That means fxy is discontinuous at the point a. So now this integral, or these two types of integrals are called improper integrals. So now here we have to find out the sufficient condition under which this differentiation and the integration under the integral sign will be valid for the case of improper integral. And that condition is this condition of uniform convergence of the improper integral a to infinity or integral a to b fxy dx. So now let us discuss this one, the test for uniform convergence of the improper integral a to infinity or a to b, where a is a point of infinite discontinuity of fxy dx. So now here let us state this, give a statement of this one first, Weierstrass M-test. Now Weierstrass M-test, using this test we can test, we can check whether the given improper integral is uniformly convergent or not. Now the statement is like this: if there x is a function m of x, that means if you can find a function of x in terms of x alone with domain to a to infinity, such that number one condition this mx must satisfy is this one, it should be a positive function for all x lying in this interval a to infinity. Number two is that integral a to infinity m of x dx should be convergent for all x greater than or equal to a. That means the improper integral as a function of single variable, that means in terms of x dx, in terms of x, should be convergent for all x greater than or equal to a. And number three is that if the modulus of this one fxy, that is the absolute value of fxy, is lesser equal to this one m of x for every xy belong to the rectangle a to infinity, that means x varies from a to infinity and y varies from c to d, then in that case we can conclude that integral a to infinity fxy dx to be uniformly convergent. So we'll follow this Weierstrass M-test in order to solve the following problems. So here the question is, establish the uniform convergence of the following integrals. Number one is integral 0 to infinity e to the power minus x squared cos xy dx. So let us solve this problem here. The first one, using this Weierstrass M-test. Solution. So first of all, let us consider this one as phi of y is equal to integral 0 to infinity e to the power minus x squared cos xy dx. Now here, what is f of xy? Here f of xy is the function inside the integral. So it is equal to e to the power minus x squared cos of xy dx. So next step, what we need to do now? What we need to do now is take the modulus of this one. Now, mod fxy is equal to mod of e to the power minus x squared cos of xy. Oh, please correct this one, there should not be the x here. So now this can be written as, using the property of modulus function, it will be e to the power minus x squared into mod of cos of xy, since mod of AB is same as mod A into mod B. Now this is less or equal to mod of e to the power minus x squared. since the maximum value of this one, modulus of cos xy, is always less or equal to 1. So in this case, you see that mod fxy, this is equal to, or this is less or equal to mod of e to the power minus x square. But we know that e to the power minus x square, this is always greater than 0 for all x belong to this interval. Please correct here, I'll keep in general this one, not from 0 to infinity. This one should be from a to infinity, okay, where a is a number greater than 0. So here, e to the power minus x square is always greater than 0 for all x belong to a to infinity. Okay. So now, therefore, modulus of e to the power minus x square will be the same as e to the power minus x square, because this term is always positive in this interval. So this will implies that mod fxy is less or equal to e to the power minus x square. Now let us take mx. Now you see that what we notice is here is that this e to the power minus x square now is a function of x alone. So let us take mx to be this one, is equal to e to the power minus x square. Then we see that what we notice is that number one condition is that e to the power minus x square is always greater than 0 for all x belong to this interval a to infinity. Number two is that integral a to infinity e to the power minus x square dx is convergent. This one here I'm just consider this one as you already know that this is a convergent improper integral, because this thing I don't know whether you have done it or not in unit 1, because there you'll have the improper integral of a function of single variable. So this is one such improper integral which is convergent. Okay, so there here I already assume that already know this one, that it is a convergent improper integral. So now this mx satisfy this condition. The first one, it is greater than 0. Number 2 is that this is convergent. Number 3 is, what is mod fxy? Mod fxy is less or equal to m of x. What is mod fxy? It is less equal to e to the power minus x square, but I've taken mx to be this e to the power minus x square. So this mod fxy is less equal to mx for all x y belong to this rectangle a to infinity, comma, then c to d. So now let us check this one. The Weierstrass M-test. Weierstrass M-test said that if there x is a function, that means if you can find a function mx satisfying these three conditions, number one, mx greater than 0 for all x belong to a to infinity, integral a to infinity mx dx is convergent for all x greater or equal to a, and then mod fxy is less equal to capital mx for every xy belong to that rectangle, then in that case we can conclude that a given improper integral to be uniformly convergent. So here you can see that since all these three conditions are satisfied by mx, therefore we can conclude that the given improper integral is uniformly convergent. So you can write here, since all the three conditions of Weierstrass M-test are satisfied. So we conclude that integral a to infinity e to the power minus x squared cos of xy dx is uniformly convergent. Now next, let us come to the second problem. We have to establish or test the uniform convergence of this integral 0 to 1 sine xy by square root of x into x minus 1. So solution of number 2. So here again, the first thing what you need to do, you denote that given integral as phi of y, integral 0 to 1 sine of xy divided by square root of x into x, not x, it is 1 minus x. Here, what is fxy? Fxy is a function inside the integral. It is equal to sine of xy divided by square root of x into x. It is not x minus 1, it is 1 minus x. Now, let us see what is modulus of fxy. This one is equal to modulus of sine xy divided by square root of x into 1 minus x. Now here our aim is to find that function mx, that is a function in terms of x, where this mod fx will be less than or equal to that mx, and also mx satisfy all those three conditions, the other two conditions, that is it should be a positive function, and also the integral of that mx should be convergent. So now here this is equal to this one, and can be written as mod of sine xy into mod of 1 by square root of x into 1 minus x, using again the property of modulus function, mod AB is same as mod A into mod B. Now this will be less or equal to 1 mod of 1 by square root of x into 1 minus x. Why? Because modulus of sine xy is always less or equal to 1, just like in the case of modulus of cos xy. So now next what we need to do is, this will imply that mod fxy is less or equal to 1 by square root of x into 1 minus x. Why I'm omitting this one, the modulus function here, is because since 1 by square root of x into 1 minus x, this is always greater than 0 for every x belong to the open interval 0, 1. Because in the interval 0 to 1, 1 upon square root of x into 1 minus x is always positive. So modulus of positive function will be that function only. So we can omit this modulus function here. So finally we have mod fxy is less equal to this one. So now you see that this function here is in terms of x. So let us take mx to be this one. Now take m of x is equal to 1 by square root of x into 1 minus x. Now then what we notice is that number 1 is that mx is always greater than 0, because in the interval x to in the interval 0 to 1, 1 by square root of x into 1 minus x is always greater than 0. Greater than 0 for every x belong to the interval 0, 1. Number 2, again I assume here that this is convergent because it is a convergent integral only from 0 to 1 from that improper integral of this one, improper integral of a single variable. Okay, so from there you'll see that it from unit 1 only, in unit 1 you'll see that you'll discuss this thing in detail, and you'll find that 1 by square root of x into 1 minus x, this one is a convergent improper integral. So here I assume that you already know the result of this one. So that is integral 0 to 1 mx which is called integral 0 to 1 by square root of x into 1 minus x dx is convergent for every x belong to interval 0, 1. And then number 2, and lastly, and what we notice is that mod fxy is always less equal to m of x. For every x and y belong to the rectangle, this one it is 0 to 1 for x, and for y it can be from C to D. So what is since mod fxy is less equal to this one, and then since I've taken this one mx to be this one, so we notice that mod fxy also satisfy the third condition of Weierstrass M-test, that is it is less equal to m of x. So here again, since all the three conditions of Weierstrass M-test are satisfied, therefore we can conclude that the given improper integral is uniformly convergent. So here again you can write the same conclusion, since all the three conditions of Weierstrass M-test are satisfied. So we conclude that integral 0 to 1 sine of xy divided by square root of x into 1 minus x dx is uniformly convergent. Why this integral is an improper integral? Because you can see that 0 and 1 are the point of infinite discontinuity of this function fxy. So I hope it is clear now, using this Weierstrass M-test, how to establish the uniform convergence of the given improper integral.